So let's actually try to show that two sets are equal. So here are our sets. And what we have is set S here, which is the set of all n, such that n is an integer and n is even. Okay, and T, which is the set of all 2n, such that n is an integer. Okay. Now, one kind of tricky thing about that is we're saying n is even. What exactly do we mean by that? And there's a lot of things that we could mean, but what I want to say here is that the remainder, when we divide n by 2, is 0. Okay. So that's what we mean by quote even. Okay. And in a certain sense, this proof is going to boil down to the fact that if the remainder when we divide n by 2 is even, then it has to be an integer k such that n is equal to 2k, right? So that's going to be the gist of the proof, okay? But the focus here is not on numbers or evenness, it's on sets, okay? That's what I want you to consider. So let's look at it. I want to show that two sets are equal. So what does that mean? I want to prove this property. For all x, if x belongs to set S, it also has to belong to set T, and vice versa. It's an if and only if, right? So how are we going to prove this logical statement? Well, the same way that we proved everything in this class. For all x, we're going to remove that quantifier. It's already at the front. It's already been renamed, right? So we can call it x naught. X naught is our constant. So we end up with this property here. X naught belongs to S if and only if x naught belongs to T. Now remember, x naught belongs to S is a predicate. So this is like proving P of xs if and only if Q of xs, right? So what we'll do is we'll break that if and only if into two parts. So we have part 1 and we have part 2. And part 1 is the if part. If x naught belongs to S, then it must also belong to T. And the other part, second part, is the only if part. If x belongs to T, then it must also belong to S. Okay, so that's the proof story. Let's do it. Okay, so here's how the proof might look. We start here, right? X naught belongs to S implies that x naught belongs to T. And what we do is we say, what does it mean for x naught to belong to S? Well, that means, remember, here's the definition of S, okay? So if x naught belongs to that, then x naught must belong to Z, and x naught is even. That is just, I have a set that's defined by a property. I have an element that belongs to the set, so that element must have that property, okay? All right, so then we replace even with the remainder property, right? So the remainder of x naught when divided by 2 is equal to 0. That's what that says. That means that x naught is equal to 0 modulo 2. Modulo 2 means according to remainders. Okay? And after that, we take that equals 0 mod 2 and we rewrite it like this. Okay? So what that really means is that 2 times x naught divided by 2 must be equal to x naught. Okay? Now, you might be thinking, isn't that obvious, right? I mean, the 2's cancel, right? And actually it isn't. It's a little bit more subtle than that. What we have here is known as the quotient remainder theorem, and that's really a fancy term, right? But here's what we have. Okay, this is something that you've known since probably 3rd grade, and you've forgotten because you've learned other stuff since then. Okay, so in particular, the quotient remainder theorem tells us that when we divide two numbers, A and B, okay, what we get is Q and a remainder R such that A is actually equal to B times Q, okay, plus R, right? That's the remainder, okay? And we have the quotient. And we have some requirements of that. The quotient has to be an integer, okay? And the remainder is between 0 and B, okay? So for instance, if I divide, let's try 12 divided by 5, okay? Then what we'll get is Q is equal to 2, and in this case R is also equal to 2, and that is because 12 is equal to 5 times 2, there's our quotient, plus 2. there's our remainder, and notice that 2 in fact is between 0 and 5. Okay, so that's the quotient remainder theorem. And again, I really need to emphasize this. This is always an integer. Okay, so it's not going to be 5 halves. It is 2, right? And the remainder can't be, for example, a negative number. It can't be -3. It also can't be a very large number like 17. Okay, so that's the way. That's what this theorem tells us. So what we have here is x0 divided by 2. That is an integer. Okay, and I notice that it's just 2 times that. There's no plus remainder. That's the part that we're saying remainder is 0. Okay, now that we got that part, then we're going to open up the other set, right? So x0 belongs to t. T, again, is defined by a property, but now we also have that kind of pattern. So we have it, well, there must be an n that belongs to z, and x0 is actually equal to 2 times that. Here's the pattern, okay? All right. We keep doing exactly what we've done before. We'll take our quantifier and we'll migrate it to the front, okay? It's on the right-hand side of an implication, so it just pulls out. And now we remove the quantifier, okay? When we remove the quantifier, then we want to choose something that's going to make the proof go through, right? So what's the proof going to involve? x0 is equal to 2n. Well, look at that. We already have that here, right? So so this is our choice of n, right? And you see that right here, right? N has become x0 over 2. That was our choice. That's the creative part of the proof. And then after that, we're just going to get 2 true, okay? So that's the proof, right? That's it. Okay. Now let's see. We're not done with the entire thing because we only proved the if part. We also have to prove the only if part, and that, well, we're just going to do that in the homework assignment. Okay. So you'll get to do that part. It's going to be very similar. Make sure that you look at all the steps, particularly where we open up these definitions of the sets. And you should be able to succeed. So give it a shot.